Hey guys, so today is our last section of our chapter 6 and it's on linear programming, and basically it's the same stuff that we were doing in the last video, except we have some different definitions that we need to go over, like maximizing and minimizing. So we're doing everything the same. We're graphing the system of inequalities. We can look for possible solutions, but our main goal is to do this thing called optimizing. So let's start with the definitions again, our last set of definitions. So linear programming is the process of finding the feasible region, which you know how to do, and determining, this is the part that's different, determining the point, the single point that gives the maximum or minimum value to a specific expression. Okay, so when we are finding that maximum or minimum value, that applies to these definitions here. So minimizing is finding the minimum value. And obviously maximizing is finding the max value. Optimizing just means finding the max or min value. So optimizing means minimizing or maximizing. And then lastly, our objective function is that specific expression that we are talking about here in the linear programming definition. So it's the specific expression you use to optimize. So these are ideas that we'll be discussing in class. They don't necessarily apply to this example that we're doing, but you need to have these down and you need to know what optimizing is. But we'll go into this word problem here that's a little bit more complicated than what we did in the last video and what we did last class. It's a longer word problem, and then at the end it asks us a specific question about a possible solution. So make sure you're writing this down, and before you start, you need to have at least 2 different color pencils or 2 different colored markers so that you can see the double shaded region when we shade with our inequalities. So let's read the word problem. Coach Mike regulates the length of aluminum baseball bats used by Howard County's high school baseball teams. According to the regulations, the length of the bat minus the weight of the bat cannot exceed 3. The lengths of bats available for purchase range from 29 to 35 inches. And then like our last piece of information here is a local sporting goods store sells an aluminum bat that is 32 inches long and weighs 28 ounces. Don't worry about that last sentence. That applies to our part C on the back after the graphing. So first, let's identify the variables and the inequalities. There are 2 variables like we've been working with, and there are 2 inequalities. So what are we talking about? We're talking about the length of the bat and the weight of the bat. So that's going to be my x and that's going to be my y. Those are my 2 variables. So x is length, y is weight. And we'll be labeling those on our axes when we graph the feasible region. All right, so I'm going to use a different color marker to differentiate between my inequalities. So my first inequality I get from that sentence right here. So the length of the bat minus the weight of the bat cannot exceed 3. And my inequality that illustrates that is x, length minus weight, minus y, cannot exceed 3. So it can be less than 3, it can be equal to 3, but it can't be any more than 3. So we denote that as less than or equal to 3. And then our second inequality has to do with the next sentence. So the lengths of bats available for purchase range from 29 to 35. And this inequality is going to look a little bit different because there's 2 symbols, but basically it's written like this. So It's between 29 and 35, the length. So length is x, 29 is less than or equal to x, is less than or equal to 35. So it can be equal to 29, the length can be equal to 35, or anywhere in between those numbers, nowhere further on the outside. So that's my system. Okay, so let's flip over. And I'm just going to rewrite my inequalities so you guys can see them here. Okay, so you guys know how to graph these. The problem with the first expression is we need it y equals mx plus b. So I can subtract x from both sides. And then I have to get y on its own, so I divide by -1. And with inequalities, if I divide by a negative number, I have to flip my symbol. So this changes into y is greater than or equal to x minus 3. And my m is 1, and my b is -3. So the way we interpret the one in red is we have two inequalities. There's two symbols, but we combine them when we graph. So let's just look at this as x is greater than or equal to 29 and x is less than or equal to 35. I'm just piecing them apart. X is greater than or equal to 29, reading that backwards. And I have x is less than or equal to 35. So that's my second. All right, so let's graph these. First, I'm going to label the axes. I'm going to follow the directions. So my x's are my length. And my y's are my weight. And I'm not going to count by ones on here just because I'm looking at this inequality here and I have a 29 and a 35. So I'm not going to count by ones because then I'll go off the graph. I'll need more room. So I'm going to count by fives. So here's my 0. Then I have 5, 10, 15, 20, 25, 35, 40, 45, 50. And then I'll do the same thing on the y-axis to be consistent. Okay, so the first thing I noticed though is that when I graph my first inequality, my b is -3. You guys know that this is only the first quadrant of the coordinate plane. I can't have negative length and I can't have negative weight. So I'm going to ignore that negative y-axis and the negative x-axis, and that's why I'm only looking here. I do have this b equals -3, which I need to graph. So I'm just going to count that down here and draw it myself. That's a -5. So although we do have a -3b, I will still have a line that's in this positive area right here that I can look at. So I'm going to just check. That's -1, -2, -3, -4. 1, 2, 3, 4. 1, 2, 3, 4. And it's really important to be precise here because we have this C question that requires us to look at a point. So you have to be precise with your line. Okay, so let's go back to blue. I'll keep this open. Okay, so my b is -3, so I put a dot at -3. And my slope is 1, and that means the same as 1 over 1. So I'm going up 1 over 1, up 1 over 1. But my tick marks are so slow. Okay, 1 is the same thing as 5 over 5. Okay, 5 divided by 5 is 1. So I'm just going to go up 5 over 5 to save time. So 1, 2, 3, 4, 5 over 5. 1, 2, 3, 4, 5 over 5. 1, 2, 3, 4, 5. 5. And I'm going to draw another one. I have my 5 over 5 on my b at -3. So I'm going to draw a solid line because it's greater than or equal to. That equals to makes it a solid line. So draw a solid line from those points. It's going on forever, so I'm going to draw arrows at the end. All right, so now I'm going to label my line before I move on. So y is equal to x minus 3. And then, of course, I have to do my shading, and then it's greater than. Greater than means shading above, less than means shading below. So greater than means I shade above. Everywhere above that line. Okay, so let's move on to the red. So I'm just going to look at this as two parts, but I'm not going to shade just yet. So I have my x is greater than or equal to 29. So I'm going to graph x equals 29. So at my x equals 29 is right here. So it's a solid line because I have an equal to. So line right through that point. Okay, it's going on forever. I draw my arrows. And then I have x equals 35, which is right here, exactly at a spot on the x-axis. Okay, so here's how I do my shading. I shade anywhere on the x-axis greater than 29, so everywhere here, and I shade everywhere on the x-axis less than 35, which is from this point and on. So basically that area is just this area in between the two lines. So I'm going to shade here. Everywhere in between there. And now you can easily see my feasible region, which is the double shaded area. So I'm just going to highlight this in blue and black so you can easily see this is my feasible region. Okay, so we found the feasible region. And normally, like what we did in the last video, I would ask you to find like the vertices, and I would ask you to find those exact coordinates, which ones are possible solutions, and then which points inside the feasible region are possible solutions. But this problem isn't asking us for that. It's actually asking us if the point that they give us in the word problem is a possible solution. So if we go back to that first page, that last sentence is what we're dealing with in C. So a local sporting goods store sells an aluminum bat that is 32 inches long and weighs 28 ounces. Okay, so if you look at this, 32 inches long is the length, that's my X. 28 ounces is the weight, that's my Y. So this is just a point, 32, 28. And it's asking us if this particular aluminum bat that is 32 inches, 28 ounces, can be used by a high school player in Howard County. Now, the feasible region shows you if that particular weight and length combo can be used in Howard County. So I look for the point 32, 28. So 32 is about here. And then I go up to 28, and that's here. So if you notice, my point 3228 is in the feasible region, which means that that aluminum bat that is sold at the local sporting goods store with the length 32 inches and weight 28 ounces can be used by a high school player in Howard County. And that's because this point is in the feasible region. In the feasible region. So yes, it can be used by a high school player in Howard County. So that concludes this video on our first part of linear programming, and we'll be continuing the optimizing ideas in class. Thank you for watching.